Okay, welcome back. I see you worked hard for your test, but you all failed. That's me also. So okay, so welcome back on the second lecture on transport. We'll take over where we were, namely in the derivation of one of the important formula for conductivity, which is the Kubo formula. And I reminded you yesterday of the very general formula of linear response, which is valid whatever is the system, whatever is the Hamiltonian, whatever you are doing, provided you only want to know small deviations from equilibrium. So we want to perturb a system very little away from equilibrium, which is in condensed matter certainly what I would call 90% of the measurements that were done. Now there is more and more out of equilibrium aspects that are explored, but I would say if you measure conductivity, if you send neutrons or X-ray to a system, that's very, very small perturbation. And essentially the linear response, which is again valid, it's a pure consequence of quantum mechanics time evolution. And if this is accepting to move, this is even better. It tells you that if you measure the average of an operator at time t, and again, I've chosen an operator so that it's averaged when it's unperturbed is 0, but you can easily shift any operator by a number, so I just subtract the average in the unperturbed state. If I measure the density, the average density unperturbed is non-zero, but I subtract the unperturbed density. So this is 0, and then it's simply proportional to the perturbation with a matrix here, a coefficient, which is dependent on the properties of the system. And the remarkable thing is that you can relate this susceptibility, this response, to essentially the correlations of the fluctuations of the operator A that you're trying to measure with the operator O that you're trying to, that is causing the perturbation. So if these two operators are completely unrelated, their commutator will be 0 and the response will be 0. But if there is a connection between these two operators, then the system will respond with more or less enthusiasm to the perturbation. This theta function here is just, it's there from the calculation, but it's there because of causality. The response of the system cannot happen before the perturbation. So you can influence a system at all later times, but you cannot influence a system before you apply the perturbation. So these susceptibilities in real time have a theta function, which says that if you measure at time t1, you're only sensitive to perturbations you applied at time t2, which were anterior to the time t1 at which you do the measure. You don't care, it's there, it comes from the calculation, but it's important to keep this in mind. Causality is, of course, totally enforced. Okay, so who tried the exercises? Yeah, don't answer all at the same time. Huh? No. So seriously, the first one, the one on what is the operators A and O for the measurement of the conductivity. Was suggestions? Yes? Go. No, I thought you were raising your arm.
Maybe.
Yes?
So you said A is current. A is current.
A is current. Yes.
O is density.
Okay. Maybe. Let's see. Yes.
Yeah, that was my second option.
The vector potential is not an operator. It's the perturbation you will apply. So this is lambda, if you want. The vector potential will be lambda. It's the thing you control from the outside, and it's the perturbation you apply on your system. But this vector potential couples to something in the Hamiltonian, and the question is, what is this something? So we'll come to it. Okay, we'll try the second exercise, which was a nasty one. No? Nobody? So let me just give you the... Yep.
I tried, I haven't succeeded.
Okay. Damned. Okay, so for the second exercise, I can give you the answer. If you go on my webpage, there is a link to a course on solid-state physics, which is in English, don't worry. And if you go to this course, if you click on this link, you have the answer to the exercise. So if you go there, you will also have the full linear response derivation as well, which I didn't do. But if you want to see how this is derived, you will have the full derivation, and you have the answer to the exercise, which is simply applying the linear response formula that you derived before and injecting it in the expressions. Okay, so here is the response to the second exercise. Okay, so let's go back to the first exercise, and let's now look at the specialization of the linear response formula to the conductivity. And there are several ways you can do this, but I will do it with the vector potentials. And I think that's the most easy way to do it. Don't ask me why he drew the line here and this horrible line there, but I'll try to do better. Voila. Okay, so the question is, how can I put an electric field to get the current flowing in the system? Because the conductivity, I remind you loosely, is essentially J, let's say at some point x and at time t, is related by, again, the usual integral over x prime and t prime to the perturbation here, which is the electric field at point x prime and t prime. So you put an electric field in the system, and this induces a current in the system. And of course, in frequency and momentum, this is a diagonal expression, so that's why we'll stay in frequency and momentum. It's much more convenient. Usually what you call the conductivity is the response to a uniform electric field. You assume the electric field is uniform, so this means Q equals 0. If you have something which is a constant in space, the Fourier transform is at Q equals 0. So usually what we call the conductivity is sigma at Q equals 0 and at a finite frequency omega. But you can also decide that you want to know the conductivity as a function of Q. That's just to tell you what is usually done in the system. Okay, let's assume we have 3 particles, and I want to put an electric field. There are 2 ways I can do it. I can put a potential, V, and this potential will couple to density, with a little problem, is that if I have a constant electric field as a function of space, how will my potential be? It will be linear. So I will have a potential which is like this. And then I will have the end of my system. And the end of my system, I have to choose how I end my system. Now, I can put the reservoirs, as we discussed, but if I don't want to do it, I just want to look at an isolated system, I have to either put the system in a box, or I have to put periodic boundary conditions. Usually, that's the 2 typical conditions that people look at. Now, if I put a box, then if I do this, there is no problem. But then I have a problem, because I cannot have a current that will flow in the box. At least after a while, all the particles will accumulate on the side of the box, and certainly at long time, I cannot have a current which will flow. So the box is not very good to study a current in response to a uniform potential. It would be much better to be on a ring. So it would be much better to have periodic boundary conditions, because now I can have my current, which will flow eternally, but I have a problem, is that this is not something that I can put with periodic boundary conditions. So using the way to implement an electric field by putting a potential is badly adapted to periodic boundary conditions. And you will enter in trouble if you try to do this, and you can solve these troubles, but you certainly, with a periodic boundary condition, it's not the best way. So let's put an electric field by putting a gauge potential, and using the other relation between the gauge potential and the electric field. So do you remember what is the relation between, if I have a gauge potential A, which depends on space potentially and on time, what is the relation between the gauge potential and the electric field? Yes. So essentially, the electric field, E, is simply dA dt. Which means that you cannot put a gauge potential which is constant in time if you want. So naturally, it means you will study electric fields which oscillate in time or something like this. So if you want the static conductivity, the conductivity at zero frequency, you will have to take the limit of zero frequency out of this formula. But this is a much more convenient route to follow than trying to put the system in a box and whatever. We'll see how to deal with the box a little bit later. Okay, so now the second question is, how do I insert the gauge potential in the Hamiltonian? Let's say I have three particles, just three spinless particles, bosons, fermions, whatever. Their kinetic energy is p squared over 2m. Now, what do I do with my gauge potential? Yes? Yes, so you change normally P into P minus Q times A, and that's the minimal substitution. So that's the way your Hamiltonian will be modified. So let me write it in second quantization, for example, just to have you have fun with second quantization. My Hamiltonian will be the sum over K of the momentum, which is h bar K, minus QA square. I put myself, let's say, in one dimension, just for simplicity, over 2m. And then I will have C dagger K, CK. Again, this is just to show you a nice second quantized expression. This is P minus QA square over 2m. Okay, so this is the way my Hamiltonian is written with a gauge potential. So now I will just assume that this is small, and I will expand this in powers of 8 to know what is my perturbation. Okay, so if I do this, I will have something which is H0, which is the unperturbed Hamiltonian, and then I have something which is plus, okay, let's write it cleanly. So I have, yeah, okay. Let's do it that way. So this is K squared over 2m. Now I would have terms which are minus QA times H bar K divided by 2m, and I have a factor of 2, and I have C dagger K CK, sum over K. And then I have a term which is Q square A square divided by 2m, and then C dagger K CK with the sum over K here. Okay. So now you see that if I want to look at a linear perturbation in the Hamiltonian, the term which is here is H bar K with a factor of 2. So it's H bar K divided by m. H bar K is the momentum, divided by m, it's the velocity. And it tells you that the vector potential here is coupled to the charge times the velocity times the number of particles in the momentum, which is what you would naively identify with a current. So actually this term is nothing but A scalar J. And I'm lying to you, so keep in mind that I'm lying to you at the moment. And if someone checks where I'm lying to you at the moment, you should tell me. But we'll correct this expression a little bit later. But essentially, the vector potential in the energy is coupled to the current. So it tells you two things, by the way. If I want to determine the current, I can do it by differentiating the Hamiltonian with respect to the vector potential. This is convenient when the dispersion is not K squared over 2m. Let's say you are on a tight binding Hamiltonian, and the dispersion is cosine K. What is the current? Well, you change K into K minus QA, H bar K minus QA, so K minus Q over H bar times A, and then you differentiate once, and on the tight binding, the current is the sum over k of sine of k times c dagger k, ck, which is the differential of the cosine, which is in your, so there is a minus 2t here, so there is a 2t times this. Okay, so what I'm saying is that this formula is quite generic. If you know the expression of your Hamiltonian in terms of the momentum, you then do the minimal substitution, which is known as the Payol substitution in condensed matter, thanks to Mr. Payol's, and then you get your current. So of course, this is in the limit where A tends to 0. This is the current. And as I said, I'm slightly lying on one point, and okay, keep that in mind. Okay, so let's imagine that we have this, and let's compute what the conductivity should be. So you see that now we have the answer of what we needed to obtain. The operator A we want to measure is the current. The operator O we want to, which is causing the perturbation, is actually the current as well. Okay, so what I can write is that the current, the average of the current at Q and omega is linked with this susceptibility chi of Q and omega to the perturbation, which is A of Q and omega, and there are minus signs and whatever that I'm not worrying too much here. And the susceptibility chi of Q and omega is the Fourier transform of minus I theta of T1 minus T2 times the average of the commutator of J of x1 T1, J of x2 T2, and this is the Heisenberg representation, and this is computed with the Hamiltonian H0. So you need to do the Fourier transform in space and in time of this object. If you have a system which is invariant by translation, it only depends in one coordinate and one time coordinate, which is the difference between the two. Okay, but that's not the conductivity. Because you see, we did the right thing. We define the current as a function of the perturbation, which is the vector potential. But these stupid guys in the 16th, 17th, 18th, 19th century, they didn't know about vector potential, so they took the conductivity as a function of the electric field. So we need now to change the thing to the electric field, but there is no problem because we know that the electric field is dA dt. And if I go in Fourier, this means that A of omega is nothing but I omega times A of omega. And so with that, you see that if I replace A by E, I have to divide by I omega. And so the conductivity, sigma, of, let's say, Q and omega is the Fourier transform of, let's say, multiplied by 1 over I omega. So let me write it just with the Fourier transform in time. So this is minus I here, which is in the definition of the thing. I have a theta function, so I need only to integrate from 0 to infinity over the time. I have to do the Fourier transform, so exponential of I omega, and I will leave a little something here, t. And then I have the susceptibility, which I wrote before, which is J of, let's say, Q. I do it already. I did already the Fourier transform in space, and T, and J hat of Q, and T equals 0 just by choosing the origin of time at 0. And this is computed with the Hamiltonian H0. And if you want, usually you take Q equals 0 in the expression. And there is a minus I here coming from the definition of the susceptibility. Okay, so this is what one would get if one was doing the thing. Now, why did I leave here a little omega plus something? Keep in mind that we don't have a perfectly sinusoidal perturbation. It has to die at time minus infinity. And remember, I multiplied it by this factor exponential delta t. And when you do all the gymnastics here, what you have to do is put back this factor here, just to ensure that your perturbation is dying where it should die. Sorry. So plus I delta. It's a little bit tricky to see this because you would think that it has to die at time minus infinity. And here we only have positive times, but this is because we have shifted the times by using the time translational invariance. You see that if I am integrating on positive time, this thing is indeed killing the integral when the time is going to plus infinity. So there is no contradiction. Maybe the test was not that negative. Okay. Okay, so we are here. We have this nice conductivity. And now we'll compute the conductivity of a free electron system. So what will it be? Just to see. So you see, now it's a question of calculation. Now I have to compute this correlator for a given Hamiltonian H0. And in general, it's a super complicated problem. If the Hamiltonian is not free, computing this commutator is a heavy task where you have to involve Feynman diagrams. Usually you cannot sum them all, so you have to invoke your favorite approximation to truncate this thing and whatever. But technically, now you know what is the conductivity of the system. Okay? So let's do it. Let's do a test run and compute the conductivity of free particles, just free fermions or free bosons. What do you think the conductivity of free fermions or bosons should be at zero frequency? I have free particles, nothing, no obstacles. I put an electric field. What do you think happens? They accelerate, they accelerate, they accelerate. So the conductivity, which is the current, proportional to the electric field, the constant of proportionality should be infinity. So we should find infinity. So let's check it. Do we find infinity? It's not easy to see, but I will walk you through a path, and you will tell me if you agree with this path. If I have free particles, I maintain that physically the current must commute with the Hamiltonian. Do you agree? If I have free particles, the current must be a conserved quantity. If you don't believe me, take the expression of the current, which we wrote, which is this one, h bar k over m, c dagger k ck. The Hamiltonian is just h bar k squared over 2m c dagger k ck, and work out the commutator, and you will find it zero. So, but physically it's reasonable. I have free particles, the current is an invariant of the system. So the current commutes with the Hamiltonian, which means that if I look in Heisenberg representation, I have exponential of I h0 t j exponential of minus I h0 t. I can make this commute through the current, and this is just j. Doesn't depend on time, which is physical. Again, you say I have a current in Heisenberg representation, it commutes with the Hamiltonian, so it's independent of time. Okay, but then it means that my commutator, which was j hat of whatever, let's say q equals 0 and t, and j hat of q equals 0 and 0, is nothing but the commutator of j of q equals 0 with j of q equals 0. So this is 0. So my conductivity is 0. So instead of finding infinity, I find that it's 0. I have free particles and they don't conduct, which is a little bit annoying. So where is the catch? It's a very subtle catch. So I guess this is why Mr. Kubo deserves his formula. We made a mistake in the definition of the current. here, I've thrown this term completely away. Which is fine. You could say it's second-order perturbation theory. But technically, imagine that in the current, there is a contribution which is of the order of A. Technically, it's a first order in the expansion. So I did a mistake because I said I will compute the current at order 0 in A, assuming that all the first order are coming from the expansion of the Hamiltonian. But that's not correct. I have a term of zeroth order of order 1 in A in the current, and this term will give a contribution which comes from the 0th order in the Hamiltonian. And I have to add both terms. So let me just correct this for you. I don't want to go into the detail. Is that the current is not what I wrote, so it's not just sum over k of h bar k over m and then c dagger k ck. This is wrong. But I have to keep the vector potential, so the current is actually the sum over k of h bar k minus qa. I still have the term here over m, c dagger k, ck. So you see that this term is coming from the vector potential, is still there, and it's modifying the current operator. So now when I compute my average, J, I have two terms. I have a term which I will call J tilde, which is the one we wrote before, and I have a term which is minus qa over m, sum over k, of c dagger k ck average. But this term is not 0. This term has a contribution with h0. So I need to keep it. It's a stupid term. It's the total number of particles. But I have to keep it. Okay? So this is the part that we computed. And this is a part that I have to remember. Sometimes it has a name in the literature. It's called the diamagnetic terms. Just don't ask me why, but I just give you the terminology in case you encounter it. But it's a term, you have to keep it. And this one, you have to do the expansion to order 1 in A, which is what we did before. So now you see that the conductivity is made of two parts. It's made of a part which is the one we computed, so sigma 1 or sigma tilde. And then I have this other term, which will be q squared times the number of particles divided by I omega times the mass. And actually, it's not I omega, but as before, I should be careful, and it should be I omega plus I delta times the mass. And now what we showed is that this term is 0 for free particles, and we are left with this term. But this term is non-zero now. Now I use the usual representation of 1 over x plus I delta. So I remind you that 1 over x plus I delta is the principal part of 1 over x minus I pi delta of x. And if you do this, you will find that for free particles, this is 0. And then this second term gives a term which is imaginary, but it also gives a term which is plus q squared times n divided by pi divided by m times delta of omega. And this is the contribution which is infinite at omega equals 0 for the conductivity. So for free particles, what we just showed is that sigma of omega as a function of the frequency is a delta function peak with a certain weight here, which people call the Drude weight here. That's 0. If I am at finite frequency, so if I'm not looking at omega equals 0, I can neglect this compared to omega, this term is always purely imaginary. So if I want the real part of the conductivity, it will only come from this one. Now, why would I want the real part of the conductivity?
In phase with the field.
Yeah, you could say it's the part in phase with the field, but it has another property. What it's representing in your system, the real part of the conductivity. Let's go back to the second exercise. You see that the energy dissipated in the system is proportional to the imaginary part of chi. But for the conductivity, there is a stupid 1/I omega factor, which is in front. So the real part of the conductivity is the imaginary part of chi. So actually, it's the dissipation. The real part of the conductivity is the part which tells you how much energy you dissipate when you do the transport. The imaginary part doesn't correspond to any dissipation. Remember your capacitor circuits or induction circuits. You had a lot of oscillations and whatever, but it was out of phase and therefore no dissipation. The real part of the conductivity is Ohm's law. It's V equal Ri, but the power dissipated is whatever, 1/2 of Ri square or V square over R or whatever. So we want the real part of the conductivity because in a way it will tell you whether you can heat your house with whatever system which is making transport or not. Okay? So here is what we get for free particles. So then one big question is, of course, and I will show you experiments, when one of the big questions is how is it modified? So it's the modification of sigma by scattering, interactions, and so on. So if I put disorder, then of course this is not true. I will change my conductivity. If I put interaction in my system, then the particle can scatter, the current is not conserved anymore, then my conductivity will be changed. One very naive way would be to say, oh, look, I had something that was, sigma was, sigma was something like, for perfect particle, sigma was something like I or minus I divided by omega plus I delta, and this was 0 plus. This is a kind of a lifetime. If now I say because of scattering interactions, blah, 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 I have a real lifetime, you would like to transform this into minus I divided by omega plus I over tau, where this is the lifetime. And then the real part of sigma will become a Lorentzian, which is essentially 1 over tau divided by omega square plus 1 over tau square, which people call the Drude form for conductivity. And it tells that the sigma of omega will be something which has a finite height at omega equals 0. That's the conductivity as a function of whatever, the temperature, the strength of the interaction, whatever. But that's the static conductivity. That's the one you would get by putting a uniform and static electric field. And then it will be broadened and extend like this with a width which is essentially 1 over tau. And this height here is tau. So if the lifetime is infinite, then the conductivity reduces to a delta function. I might have forgotten a factor pi or whatever. And if you have a finite lifetime, then it's broadened. Of course, you can imagine more complicated system where this form will be completely different. Okay? And one of the big game is to understand what is this shape and to understand what are the mechanisms that are controlling here tau, that are controlling the width, that could give you another peak here, for example, which is what you will get if you're in a Mott insulator, and so on and so forth. Okay? So that's all what I wanted to tell about conductivity. Now let me show you some experiments, because of course the idea is to measure it. I have an exercise for you. Let's assume that I have 3 particles. I have 3 particles. Let's say fermions, just to, with a dispersion h bar square of 2m. And I have interactions between them. Let's say Hubbard-like interaction, contact interaction, the typical cold atom interaction. So particle interaction is proportional to the square of the density, u square. So u times rho of x equals 0 square. This is the interaction. Or let's say, sorry, I shouldn't write it that way. I should write it better. I have contact interaction. So the is integral over dx, rho of x square. Or you have all seen the Hubbard model, I guess. Did you have something on the Hubbard model in the previous courses? Yes? Okay, so for Hubbard model, you would get an interaction which is sum over I, u, and up I, and down I. But here I don't want any lattice, nothing. I just want, so just to say it's a square of the density. And the Pauli principle tells you cannot put a spin up. That's why you don't get the n up terms. But this is a typical interaction. Now, I'm in free space, no lattice, no nothing. K square dispersion. What is the conductivity of the system with interactions? I'll let you think about it. Okay, so let me show you a couple of experiments and go back to okay, so this is experiments that were done in the group of Joseph Tewison, where he was looking at essentially 2D gas. And to measure the that's bad name, but the frequency-dependent conductivity, he used the method that I alluded to and which I didn't discuss, which is the shaking method. So I told you if you shake the amplitude of the optical lattice, it's not the conductivity, but if you shake the lattice horizontally, it is the conductivity. So actually, instead of shaking the lattice, he was in a trap, so he moved the center of the trap with respect to the lattice, which is just a change of referential compared to moving the lattice. And here is the image of this. Then you let the system do something for a while, and then you need to measure something, and then it depends which system you have at your disposal. Because the real part of the conductivity corresponds to depositing energy in the system. If you have a way to measure the energy deposited in the system, that's a good measure of the real part of the conductivity. You could also measure other observables, like the number of doubly occupied sites or whatever. But this is something that will give you an information on what is the real part of the conductivity. I don't want to go in details on the experiment itself, but here is the frequency-dependent conductivity plotted as a function of the frequency with a real part and imaginary part, which have been determined by this method. So cold atoms are quite remarkable in this respect because they allow you, by using this trick, it's not an easy experiment. You see that it's also a relatively recent experiment. It's not something that has been done, that's drift. It's not something that has been done at the beginning of the cold atoms, but you can extract this frequency-dependent conductivity out of this procedure of shaking, horizontal shaking, that we proposed with Akiyuki Tokuno a long time ago. Now, the question here is, what are the mechanisms that controls the shape of the conductivity? You see that this shape has very little to do with what I drew and sold you as a big peak which is centered around omega equals 0. Okay, so this is a very different shape here, And the only thing you have here are the interactions among the particles and the optical lattice and the trap. And so you can think, and I let you read the paper, of course, to see what are the mechanisms that are causing this type of shape. And out of this shape, there is a lifetime, if you want, which is extracted. What he calls gamma is essentially what I call big delta, or 1 over tau. And then this is plotted as a function of the strengths of the interaction. And you see that roughly this object is proportional to u square. So the interactions are directly responsible for this lifetime. So again, I don't want to go into the details of this particular experiment, but this is an experiment that aims at understanding what happens if I have fermions on the lattice. I have an interaction. What is the interaction giving for the transport properties, but of course, more generally, what it will do to the system, and that you can access through this. There is a second very beautiful experiment that was done in the group of Asim Bak in Princeton, where he was under a microscope, so he had really local capability to observe. And there he used the method of what I would call a generalized kick, but very, very, very controlled kick, because what he does is he imprints a modulation of the density initially. So it's like putting, if you want, an electric field which you know at t equals 0 exactly, and then you let the system relax. So it's a variant of what I showed you by saying you do a kick at time 0, but that's the same idea. And as a function of time, you see how the system is relaxing, and out of this you can extract the conductivity in the same way. And there the big question, this is two-dimensional, this is the Hubbard model, and so one of the big questions is what is the conductivity of a two-dimensional Hubbard model, because some people view it as the solution, potential solution for high TC conductivity. So just to show a result, here is the resistivity as a function of the temperature of the system. So for each experiment, you need to extract the omega tending to 0 part. This is dependent on the temperature. Then you plot this for various temperatures. And then you try to shoot down theorists, which is a fun game. I highly recommend it. Sorry. So here is the experimental data. Here is a result of one calculation, which is exact diagonalization on a small cluster. And the green is a result of a much more sophisticated calculation using mean field approximation, which is called dynamical mean field theory. And the conclusion of the paper is that, okay, if I had to bet, I would bet more on the blue curve than on the green curve for what is seen in the experiment. Okay, it's not the final word on the subject, but definitely it shows you that by measuring this quantity, you can, of course, filter various proposals on what the interactions are doing on the system. Okay, that's all what I wanted to show you for the Kubo, for the bulk. And now I would like to, yes?
Maybe an easy question is, if you come back maybe to Joseph's experiment.
Yes. Oops, sorry.
So if now I replace lattice with a disordered system, and then
you can do exactly the same.
it will be
Yes.
similar, right?
Yes. You can do the same. And actually, we looked a little bit at this, and it's a great way to measure the conductivity. That's, to the best of my knowledge, it was never done. Yeah, so. Okay, before I move to mesoscopic systems, are there questions on this? So again, the Kubo formula is a super general, super useful formula, but of course, it's a little bit like if you write the Hamiltonian of the system. It's not because you wrote the Hamiltonian of the system that you're going to solve the Hamiltonian of the system. Or if you say, I can use Feynman diagrams to have the expansion in powers of the interaction. You can write order by order, but you cannot resum the series. So, but it's a framework that allows you to have a very general and efficient way to compute any quantity that you might want. Again, I insist on the fact that here we were looking at something which was a simple electric field and measuring the current. But of course, you can generalize this formula in any way you want. I can put the electric field along X and want to measure the current along Y. In which case, this will be JY, this will be JX. This is what you need to do for the Hall effect, for example. I could put a gradient of temperature instead of an electric field, in which case this will be J, this will be something else, and so on and so forth. So you have a very generic framework to measure transport coefficients through the system. And again, the practical difficulty is to be able to do the calculation normally. Okay, now let me go back so again, I showed you two experiments and do the exercise. Try to think for free particles, what should be the conductivity in presence of interactions? Yes?
Sorry, I'm sure you already said it, but may I stress again the difference between the linear response step and the Kubo formula?
And the Kubo formula, there is no real differences. The Kubo formula is the linear response to an external electric field. So if you want, the general formalism of linear response is much more generic, and you could say Kubo formula is a trivial consequence of it. The two little things you have to remember is that for the conductivity, the current contains the perturbation itself, and you should not forget this extra term. Although in practice, every time you will be at finite frequency, you can completely forget it if you want the real part, because it's purely imaginary. And the second thing, you shouldn't forget there is an extra 1/i omega factor compared to the normal formula, because again, the perturbation is the vector potential, not the electric field. But except for that, this is totally in the framework of linear response. And again, you can generalize the Kubo formula as you want. Are there other questions on Kubo? Okay, so let me ask you a question. Yep, Hans-Peter? Not necessarily. You can generalize it to transverse transport, yeah. You can look in the Mahan, for example. Again, it's just a linear response. So as soon as you get something which you write as a small perturbation and you want the linear response, you have a Kubo formula for it. So you can perfectly do Kubo for longitudinal transport, transverse transport, Hall effect. As I said, if you want to do Hall effect, you put an electric field along X, and what you want is the current along Y. So then it will be the correlator JX, JY. And okay, we'll come back maybe on the Hall effect on tomorrow, but no, you can completely generalize the Kubo to all kind of transport. I think you're right for the historical Kubo formula of 1957, but okay, people moved a little bit from there, and I think it's fair to still call it Kubo formula for that. Other questions? Okay, so I have a question for you. I have a system of free particles here of length L, free. And I would like to know the conductance of the system. So what is it? So I remind you, we define the conductance as saying the conductance is the conductivity divided by L. So what should it be? If I trust Kubo formula. You told me the conductivity is infinite, so the conductance should be infinite. Okay. Then why do people see that? Because here the conductance of the system is all but infinite. It's 0, it's 1/h, 2/h, 3/h, 4/h, but definitely not infinity. So what is wrong? Okay, so rather than tell you what is wrong, let's look at another point of view for transport, which I'm sure you will feel much more familiar with, because this is a wave point of view. And now after Jacopo's talk, we know that everything is wave and can be seen as wave, but I will show you that the same is true for conductivity. So we continue in the same way. No. So you see that with Kubo, we run into a very serious problems here. Because you would say, okay, I have free particles, conductivity is infinity, I computed it, it's true, it's whatever. And now here is the measurement, and conductivity is 1 over h, or e square over h if you have charged particles. So what is going wrong? What is wrong in the Kubo vision, or what is wrong with this calculation? And this is a debate which was really making people very unhappy in the let's say early 80s. And let us look now at the Landauer Büttiker. I always forget formula. So you see, the Kubo formula is really a vision which is rooted in saying I apply an external electric field and I have a perturbation which is a current. So it's not, of course, a local response because it can encompass interactions and whatever at long range or what, but it's a kind of vision that I don't need to know what are the boundaries of my system. I have a kind of electric field here in the system, and then I have a local current here, J. And in a way, this relation is there, and I don't need really to know what are the boundaries. I told you, well, let's take periodic boundary conditions or whatever, which is certainly not realistic in any experiment. Well, I mean, you have to devise an experiment which is really designed to have periodic boundary conditions, and there are cold atoms experiments with rings, but they are not that common. And so this is the point of view of Kubo. And now we could have another point of view, which is let's take seriously the fact that we have two reservoirs, one on the left, one on the right. And so I have really a set of free particles here with energy levels which will be filled up to a chemical potential, which I would call mu left. Then I have a system here. And then I have a system on the right here with energy levels which are less filled, with a chemical potential mu right. And of course, I want that mu left minus mu right is essentially the charge times V, the voltage that I would apply if I have charged particles, or simply this is the chemical potential difference if I don't have charged particles. And then particle can connect between there, go in the system, and go to the reservoirs. And that was the vision that Rolf Landauer had of conductivity, is to say conductivity is like the transmission through a waveguide. So if I have free particles, the energy is conserved. It's not true if you have interactions. So the application of Landauer-Büttiker formula to interacting system is complicated. I mean, it can be done, but it's complicated. But for the moment, let me ignore this. So it means that I can imagine the left reservoir sending waves through the system, and the right reservoir will receive a couple of particles or waves, if you want, on the other side, and a certain part will be reflected to the system. So I can imagine something where I say I have a plane wave which is going here with an energy E, and this part will be transmitted and a part will be reflected. And in a way, I should be able to relate the current to this coefficient of transmission. So let me call T of E the transmission coefficient. Again, if I want to practically compute this transmission coefficient of the system, it's not necessarily trivial. if I have disorder, for example, in the system, or if I have a sequence of potentials here or whatever. You all know in quantum mechanics that it's not an easy task, but it's a relatively well-defined task. You take your system, you solve Schrödinger equation with the proper boundary conditions and whatever. Okay, now let's compute the current which is going from the left reservoirs to the right reservoir. So what is this current? The current will be the velocity of the particle. The current is always rho, the charge, the density of matter or the density of charge, times the velocity of the particles. So this is the velocity which will depend on the wave vector k. So this is the current per wave vector k. And then I need to know what is the number of particles which have been carrying this current. Well, the number of particles is essentially the number of particles which could actually be transmitted on the other side of the system. So this will be times the transmission T of, let's call it E of k, which is the energy of the wave with the vector k. And now I must do something which is a little bit more complicated, because I can only send a particle if the state here is occupied. If I assume I have 3 particles, I can say these states are occupied based on the Fermi-Dirac distribution. So I want that the state here, F, is occupied. So I have to multiply by the Fermi vector of the system. And I have another constraint. If these are fermions, I need to go to a state which is empty. Otherwise, Pauli principle blocks me, and I cannot go inside the reservoir. So I have to multiply by 1 minus F left. So this is, sorry, F left here, and this is F right of epsilon k. So this is the current that will go from the left reservoir to the right reservoir. Okay? Now, I have to do something which is to take the opposite current into effect, because, of course, if there is a current which can go from the left reservoir to the right reservoir, there can be a current which goes in the opposite direction. So this is the left to right. And now I can do the same thing with the right to left. So this will be the same velocity. This will be the same transmittance. But, of course, now if I want to have a current in the opposite direction, I need that the state is occupied on the right, and I need that the state is empty on the left. Which usually, if I impose a large chemical potential difference, will not be so easy. I have to climb uphill. So I have more chances to end up on a state which is occupied if I try to go that way than if I try to go that way. But okay, I have to write this. And so the total current, J total, is what? It's the sum of a k. I probably forgot a factor of q for the charge if you have charges. I have the velocity vk here. I have the transmission t of at the energy ek. And then I have the difference of these two factors. But you see that the cross product, they cancel each other. FL, F right cancel each other. And the only thing that is left is FL of ek minus F right of ek. So I have here FL of ek minus F right of ek. Okay, so that's a nice expression. And now we need to get rid of this object, which is a little bit annoying. And for that, we will remember what is the velocity. The velocity is essentially the derivative of the energy of the system with respect to the momentum. If I have p squared over 2m, the velocity is p over m. It's d e dp. So velocity vk is the derivative of the energy, epsilon k, with respect to the momentum. So this is d of ek, if you want, times h bar times dk. Okay? So I will use this. Then what I get is q here, this sum over k I can replace by an integral. It's the integral over dk. I do with reservoirs which are one-dimensional, divided by 2 pi. This is the usual quantization. Then I have here d of ek h bar dk. And then I have fl of ek minus f right of ek. And then you see that I can do the change of variable and say that my integral over k is just an integral over the energies. And I forgot, sorry, the transmission t of ek. So now I can replace this by q. I get a factor 2 pi over h bar, 2 pi times h bar, which is h here. And then I have an integral over d of the energy times the transmission at this energy times the left Fermi occupation, which is f of E minus the chemical potential mu left minus the Fermi factor on the right, which is f of E minus the chemical potential on the right. Now I could say, for example, the chemical potential on the left, mu left, and I probably forgot a minus sign because the current has to be counted properly, but let's not worry about this for the moment. So mu left is essentially, let's say, q times v over 2, and mu right will be minus q times v over 2. So I say I put symmetrically the imbalance in potential, but it doesn't matter. You can put it the way you want, just a shift in the energy. So I just raise the chemical potential by plus v over 2, and I lower the right chemical potential by minus v over 2. And then you see that the current J is equal to q over h, sum over dE of T of E times f of E minus qv over 2 minus f of E plus qv over 2. So this is a remarkable formula because it tells you that if you know the transmission of the system at any energy, which in principle for non-interacting particles you can do, you just scan the system and send waves and compute how much is transmitted or not, then you have the current as a function of V. This is not linear response here. You get the full current voltage curve. Okay? So this is a fantastic formula. Okay, is it true? We can discuss. Let's see what it gives. And let's look first what it gives in linear response. So let's do the expansion in linear response. So if I just do linear response, which means that I can assume that V is small, then f of E minus qv over 2 minus f of E plus qv over 2. This will be qv over 2 minus minus, so plus qv over 2 times the derivative df dE, which is essentially at zero temperature a delta function if I have fermions. And so I'm saying that the current will be something like q squared over h times v times, if I am at t equals 0, I could say that df dE is minus delta of E minus EF. And as I said, I forgot a minus sign somewhere when I was doing the current. And then this is the transmission at the Fermi energy of the reservoirs. So the linear response tells you, with the Landauer-Büttiker formula, tells you that the current is proportional to the voltage, at small voltage, with a prefactor, which is the conductance. So it tells you something very different in appearance from Kubo. It tells you that the conductance is q squared over h times the transmission at a certain energy for the reservoirs, which is the Fermi energy of the reservoirs, if you fill the reservoir up to EF. And this is remarkable. Because what does this tell you? It tells you the best you can do for the transmission is 1. You cannot transmit more than what you send. So it means the maximum value of the conductance you will get, even for a perfect system, will be Q square over H per channel of transmission. So we get a very different result than what we got from Kubo, apparently. And of course, you can imagine that this made people go mad before. But this result is in very good agreement with what we saw in the experiment. Let me show you here. So this was, I should have shown you, sorry, I took a slide where only the cold atom results were shown. I should point out that this quantization of conductance was measured much earlier in condensed matter, of course, in constriction channels. So it's not something which was discovered in 2015, but something which was known till, forgot the precise date, but 1987 or something like this in condensed matter. But so what is the reason why seeing these plateaus here in the conductance? Why do I see 0, 1, 2, 3 here? Exactly. In the little wire, which is here, we get various modes of transmission. Remember the modes that Jacopo told you about? Well, it's the same here. Because of the finite size, you get quantization of the transverse degrees of freedom. So you get one free band at k perp equals 0, one free band at k perp equal 1, one free band at k perp equal 2, and so on. And when you change the chemical potential in the channel, which is what they call the gate potential here, initially you have 0 channel of transmission, so conductance is 0. Then you enter a place where you get a good transmission through this channel. You get a little worry here at the entrance because also of the finite temperature. The dF dE is not a delta function, but is a blurred object. And then you are in this channel of transmission. You get conductance, which is 1. Then you enter in the second channel of transmission, and the 2 channels add in parallel. So you get conductance 2. Then you go, and so on and so forth. And the conductance is quantized in unit of 1 over h. For neutral particles, there is no Q which comes between potential and chemical potential. So this is what you get. So this is a fantastic formula because it allows you, for non-interacting particles, to compute transmission through a barrier of finite length L. It also kind of validates Ohm's law for many systems because you could imagine that if you double the length, you divide by 2 the transmission. You also know that this has good chances to be wrong. And you know a lot of systems where if you double the length, the transmission will be divided by much more than a factor of 2. I don't know if you heard about Anderson localization, for example, but if you put disorder in the channel, the transmission will be affected much more severely. If you have a Mott insulator in the channel, the transmission will be lost exponentially fast, which means the conductance will not vary inversely proportionally to the size, but with much more violent variation. Okay. Where is the catch with Kubo? That's a difficult question. So this is in agreement. So this leads in particular to conductance quantization. And of course, if the transmission is not 1, in principle, you can compute the transmission. So what is the catch with Kubo? And we'll finish with that. It's a relatively subtle one. And it took a long time for people to understand. Actually, both are perfectly consistent. And both are giving the same answer. But you have to be very careful of where you measure the potential. Let's look at the voltage, V, as a function of x in this system. So I have the left reservoir here. I have the right reservoir here. And I know that in the left reservoir, the voltage is plus V over 2. So let's say V over 2. I know that in the right reservoir, the voltage is minus V over 2. I also know that I have a perfect system. If I have a perfect system, the resistance is 0. So what is the voltage drop in the system? It's also 0. I have no reason to drop the voltage. So the voltage drop has to be 0. But then I cannot connect these two. I would connect easily if I had something like this, which would mean a voltage drop which is linear, which would mean a finite conductivity. So the only solution, and you can support it by calculation, is that the voltage drops at the entrance to the system, like this. People call this the contact resistance. This is the resistance which will be generated at the entrance, at the exit of your reservoir, and at the entrance to whatever is your system. So this is voltage drop. Ah, this is really annoying. And now you see that the resistance of the system is the contact resistance of the left reservoir plus the resistance of the system plus the contact resistance of the right reservoir. And actually here, there is no electric field. The voltage is constant. So your conductivity might be infinite. There is nothing that will take place here because there is simply no electric field, no voltage drop. So actually, if instead of measuring the voltage from the reservoirs, so Landauer-Büttiker is doing what people called a two-point contact measurement, where you take the voltage from the left reservoir minus the voltage from the right reservoir, and you compare it to the current. If you do this, you get that the conductance is Q square over H per channel. Kubo is actually measuring to the local electric field which is inside the system. And so what you would need to do is to put detectors here and here, and then check what is the voltage drop between these 2 points. And then you will find it's 0, which means the resistance is 0, which means the conductivity is infinite, and that's consistent. So Kubo is doing what people call a 4-point contact measurement, where you measure the current based on what goes from the left reservoir to the right reservoir. There are 2-point contact. And then you need 2 other contact points inside the system to measure the voltage drop. And of course, perfectly transmitting systems are peculiar enough that it makes enough difference that all the resistance is contained in the contact resistance. If you had a diffusive system, this resistance would be kind of proportional to the length of the system. And for a long system, it would simply dominate completely. And then you can forget about the contact resistance. And when you divide by the length, you would get the same result. So this difference, which is very subtle, is coming because you can devise systems which are near perfect conductors. And in the near perfect conductors, it's very important where you measure the voltage and not mix these things. Nevertheless, the Landauer-Büttiker formula is a remarkable formula which allows you to view again the conductance as a transmission of wave through a waveguide, which is the system. Okay, I'll stop here. I just want to flash one experiment to you. We'll discuss it more tomorrow because I will leave it with you as an exercise. Let's now imagine, so this is experiments which were done in the group of Tillman and Slinger, by Martin Lebrun in particular. Now, instead of having the system, which is a nice tube which transmits perfectly, which is what you saw before, let's put a periodic potential on the system, which can be done by putting light on the system. So here is the periodic potential, which has been superimposed to the potential which is inside the tube. What do you think the conductance will do? Will it show the same plateau and whatever plateau than before? I'm afraid the next slide will give the answer, so I'm not showing it, but I'll try to flash. Yep. Let's forget that. Yeah, here it is. Yeah, you have the answer on the top of the slide. So here is what the conductance does. This is the experimental system. Forget the other curves. Let's look just at the blue one, which is the one with many periods. It starts at 0 as before. Then it wants to go to 1. Then it goes down. And then it starts again. So I leave you as an exercise for you. Why? Why is it doing this? And what is causing the reduction of the transmission, which you see on the theory side here? You see this curve. It's going down here, then it's going up again. And here is the plateau at 1. By the way, these curves are computed with the Landauer-Büttiker formula. And these are the transmissions through the system at various energies. Voilà, so I leave it to you as an exercise. What will happen if you have a channel which has a periodic potential in it and you try to pass free particles through it? Voilà, let's stop here and I gladly answer questions if you have. This was a little bit more dense than the session of yesterday, but I think it was important to see these two very, very fundamental formulas for the transport, because more or less everything one does after is a variant on these formulas. Of course, there are generalization of the Landauer-Büttiker formula to interacting system. If you want to know more, you can ask Joao, who is here. There is something called the Mayer-Wingreen formula, which generalized this to interacting system. You can use also more sophisticated techniques like Keldysh, which was already mentioned by Jacopo, which I will tell very little about. But essentially, the philosophy is always more or less based on one of these two representations for the transport. Voilà, we stop here. Tomorrow we'll finish the story. I will show you the total answer of the periodic system with interactions, because for the moment I ask you to guess what it was without interactions, but the good thing about cold atoms is you turn a knob and then you get the interactions. And then we'll discuss about either disorder or Hall effect. I've not yet made my mind, so if you have a popular wish on one of these two topics, let me know, and I'll try to accommodate. And meanwhile, do you have questions? I lost everybody. Yes?
Can I ask you to explain again the 4-point conductivity?
Yes. So there are two ways you can do a measurement of the conductivity. You can say, I have my reservoir here, and I have my system. Now, in the reservoir, you can measure the voltage here, V left, V right, and of course, you know how much current is passing through the system. So you use the two reservoirs both as a measure of the current, but also as a measure of the potential. Now what you could do is another experiment where you have still contacted your system like this, but now you put other systems here, and these systems allow you to determine what is the potential here at position 1 and the potential at position 2. These systems are sufficiently isolated here by tunneling, for example, so that there is a very, very small fraction of the current which is lost inside these systems. If you have, for example, a very high tunnel barrier, you can make sure that this is the case. You get very good current which is going here, and always a finite but super small part of the current which is going here. In which case, you have a 4-point measurement where you use 2 of the points to measure the current which is passing through, and 2 of the points here to only measure the potential. And this is something that will give you direct information on what is the potential inside the system, which, as we saw, because of the contact resistance here, is not necessarily the same thing than the potential in the reservoirs. And this is particularly important when you get something which is a perfect conductor, because then a lot of voltage drop can occur between the contact of the reservoir and the entrance to the system. If you want to use Kubo, in a way, you're only sensitive to what is inside the system. If you take the Landauer-Büttiker formula, it implements from the start the presence of the reservoirs. So you can treat this situation much more easily. But again, you're limited in principle to non-interacting particles. And again, you can modify the formula to deal with it. There are situations which are even more complicated. I will give you one which was actually measured in Saclay in the group of Michel Devoré and Daniel Estève, which is what happens if you have a system here with a voltage V1, a system here with a voltage V2, and you have a system here which is diffusive. So you have a lot of disorder scattering. So normally you expect a voltage drop like this, where you go from V1 to V2, and that's perfectly okay. So if you measure the distribution of particles here, you would expect to see a Fermi factor with a step function at the voltage here, which I would call V of x. On the left reservoir, you would be at V1. On the right reservoir, you would be at V2. And here you would have a Fermi factor of distribution of energy, which would be going slowly from this value, then you reduce the potential, and then you go to the distribution on the left reservoir. That's what you expect. And what is measured is this. What is measured is, of course, at the position of the left reservoir, you have the thing here. So let me put the right reservoir here, V2, V1. And then what you see is something like this, where you see a double step. You see something like this. And you see that this thing is going down. So you start from the left reservoir, you're here, and then the double step is going down, going down, going down, going down, till you reach the right reservoir. So the two limiting values are good, but the inside is not at all what you would expect by saying you have a local potential, which is representing the potential as a function of x. And what it says is that locally you have a completely out of equilibrium fluid where the two particles diffuse a lot, but they don't mix. And what you see are the proportion of the particles from the left reservoir, which have the potential V1, and the particle from the right reservoir, which have the distribution with the potential V2. And the further you're away from one of the reservoirs, the more or less you have particles of one species. This immediately changes if you put inelastic scattering which can redistribute the energy, then you go to the other curve. So one has to be extremely careful, and again, this tells you that you need to be very careful in incorporating the reservoirs potentially in your transport theories or measurements. Yes, Jacopo?
This picture includes a self-consistent solution of the Poisson equation for the spatial distribution of the charge.
You mean this one?
Or the center, or that one, yes.
This one. Okay, so this picture first is my very beautiful and aesthetic rendering of a real experiment. So it includes whatever is in nature today, and you see very nicely this thing. This is the naive expectation of a linear voltage drop that you would expect if you have a finite resistivity. And I agree with you that in most systems this will not happen. You will have first a drop at the contact, then you will have something more complicated, then you will have a drop at the other contact. This is also assuming that you have Ohm's law, essentially that the voltage drop is perfectly linear, which is not the case if you have localization or more violent insulators. So very often this picture is simply wrong. Other questions or comments? Or everybody's, yep.
I'm wondering tunnel barrier. Is it by any mean useful to either use a Kubo, but I guess not the Kubo, but at least another particular?
Both are useful, and both have been done, and that's one thing we'll discuss tomorrow. So in a way, the periodic potential that I was showing you is putting not tunnel barriers. This has very weak modulation of the potential, but of course you can do it by putting a huge barrier. Just to answer your question with an experiment, here is the quantum point contact. So this is the two systems, the two reservoirs. And now here you have a huge tunnel barrier in between. And these are the curves that you see for the current as a function of the voltage, the bias. And these are very weird curves, which are practically the current is constant. But I'm cheating because the reservoirs are superconducting. So this is something. How you compute this? Well, here it was computed using Keldysh, so neither Kubo nor Landauer-Büttiker, but yeah.
Because in the experiment from Tillman, I mean, in this case we have zero, right? You put a very high barrier.
You don't have zero, you have a small current,
Right.
and then they cannot measure.
You're using it's small, but it will be finite.
Well, it's small but finite, then the question is, can you measure it? If it's below their experimental resolution to measure, then they will not be able to measure it. In a way, you could say that this is like a tunnel barrier in this first experiment. This is like a tunnel barrier. The one on the conductance here, it's an extremely good junction. The transmission here, what you find by seeing this plateau at 1, it tells you that the transmission of the junction is 1. So this is a super good conductor. There is no barrier in it, nothing. You send a wave, it goes through the other side perfectly. So if the plateau was lower, then it would tell you that you have a bad transmission through the channel. Okay, I think we can stop here. I hear stomachs growling and things like this, and we continue tomorrow with ending this point contacts and then disorder or Hall effects.